Okay, this is going to be a short video to help you understand the rule of identity elimination. It's explained on page 56 of the textbook, and there's an important example on page 57, and then a you try it, and many people have trouble understanding the example because of the symbolism that's used to explain the rule. Okay, before I talk about the rule, I want to mention one other thing. When we're talking about identity elimination, we use the equal sign as the symbol for identity, but we don't mean equals. And so I want you to understand what identity means in language, proof, and logic. Here's an example. If you have two cubes called A and B, and the two cubes might be identical to each other in the ordinary language that we use, like they're the same size, they're the same shape, they might be the same color, etc. But they're not identical in the sense that is used in language, proof, and logic. Cube A is identical to itself, and cube B is identical to itself, and each object in the universe, and every object in a Tarski world, is identical to itself. But nothing is identical to anything else, so each object is only identical to itself. Now, if you look at these two cubes, if cube A has another name, if it's also called C, then it's true that A is identical to C, because there you're saying that the same object is identical to itself. So the sentence A equals C, and we'll sometimes read it that way just because we are using the equal sign. But bear in mind, we always mean A is identical to C. That sentence is true because A is the same object as C. It's not a different object. It's the same object. But the sentence A equals B, or A is identical to B, that's false. That's not true, because A and B are not the same object. They are two objects. Let's look at our next slide here. Okay. Let's look at how LPL symbolizes the rule of identity elimination. And here's how they do it. They say, if you have two sentences, and by the way, the formulas that appear above the little horizontal line here, that means that we've already been given them as true. They're already established. The little symbol that I put in here, which is similar to what they show in the textbook, a little blue symbol, means we have the right to state this new formula based on the first two formulas using this rule. So if you have Pn, and then you've got n equals m, then you have the right. This rule of identity elimination authorizes you or licenses you to then state Pm. Let's look a little closer at what this means. Pn means any sentence at all that contains a name, and they're using n to stand for any name at all. And then n equals m means an identity sentence that uses the same name that was in the first sentence, that was in the sentence P, then it has an equal sign, and then it has another name, which they're symbolizing as M. That means that you have the right, when you've got those first two things, you've got a sentence containing n, and then you've got n equals m, you now have the right to repeat the same sentence that was your P, sentence P, but now you have the right to substitute m for n anywhere you want to in that first sentence. Now P might contain one occurrence of the name in question, or it might contain several occurrences of that name. And what this blue arrow authorizes is you can replace one or more, as many as you like, of the occurrences of the original name in the original sentence with the new name, which is symbolized as M. Now, notice one other thing. The order of n equals m actually matters. So this says you can replace as many occurrences of the name n in the first sentence with m as you want, but it doesn't say you can replace m with n. So it goes kind of in that order. So the name that appears on the left of the second sentence has to be the one that we're talking about in the original sentence. Okay, so if line 2 said m equals n, then the inference wouldn't go through, and this would not be a correct application of the rule. Just to make this more clear, here's some examples of Pn. In other words, any sentence at all that contains a name that we're calling n. But I'm going to give specific examples where we actually use specific names. N is kind of a variable, but now we're going to use constants that are actual names in the language. So here's some sentences that could be referred to by Pn. The first one is cube d. Okay, that just says d is a cube. That's a sentence that contains a name, and the name is d. Second one, b is larger than d. Okay, that contains two names, b and d, so either one of them could be applicable depending on what the second premise of the rule is, like depending on what the identity statement is that we're going to use. So the next example, same size f as f. Now that means object f, which could be, for example, an object in Tarski's world, is the same size as itself. It's the same size as f. Now notice that in this sentence there are two occurrences of the name. So we'd be allowed to substitute another name for f for the first f or for the second f or for both. If we had an identity statement that said f equals and then some other name like d, let's say. So then we could get same size df or same size fd or same size dd by substituting d for f. Here's another one, married Jane. Now they sometimes use like ordinary English predicates like married, meaning is married, and Jane is the name, so Jane, this just says Jane is married. Okay, that's a sentence, so it qualifies as P, and the name, in this case, the N, is Jane. Okay, now later in the course, actually quite soon in the course, we're going to start dealing with more complex sentences that have operators in them like and not, and or, and if then. And so another thing that could be our sentence P would be a sentence like this, cube A or not smaller CA. Now that thing that looks like a V in the middle, that's the symbol we use for or. And the little horizontal line here with a little hook on the end of it, that's the symbol we use for not. So this actually says A is a cube or C is not smaller than A. Now that whole sentence could be our P at the top. Pn could be this sentence, and n could be A. So we're not necessarily talking about an atomic sentence here. We could be talking about a compound sentence, like this. And this sentence we're looking at right now contains two occurrences of the name A. And if we had an identity statement to the effect that A equals, something else, like D, we could substitute D for A in the first occurrence, or in the second time it occurs, or both, using the rule of identity elimination. Okay, now here's two sentences that might surprise you, and this is where the whole obscurity, this is where the kicker is, that makes this whole thing obscure to many people, and it was obscure to me the first time I read it too. The sentence A equals B could also be an example of Pn, because it's a sentence that contains a name, and Pn just means any sentence that contains a name that they're calling n. So in this case, we've got a sentence, A is identical to B, and it contains two names, A and B. So either one of those could be the n that we're talking about. And then finally, the sentence A equals A. That could also be an example of Pn. That's a sentence, so it qualifies. And it contains two occurrences of a name, A. So A stands in here for our general n. So let's look at a couple of simple examples of how to use the rule of identity elimination. And the second example will be the one that causes all the trouble, that's found on page 57. But let's look at an easier example first. So the first example is, we're given two sentences. A is larger than D, and D is identical to F. And we're allowed to say, based on that, A is larger than F. How did we get there? Well, the first sentence contains a name, namely D, that we're interested in. The second sentence tells us D is identical to F. So the rule lets us substitute F for D in the first sentence. So the second sentence is our vehicle that allows us to substitute F for D in the first sentence, and that gives us larger AF, meaning A is larger than F. And it makes perfect sense, because if A is larger than D, and D is the very same object as F, then A is obviously larger than F. So the rule works. Okay, let's go on to the next example. Here, our first sentence, which contains a name, is B is identical to B, or B equals B. Now, we're allowed to write that sentence anytime we want. We can always introduce into a proof any statement that has the same name on both sides of the equal sign. So like B equals B, or F equals F, or Jane equals Jane, or whatever. And the rule that lets us do that is called identity intro, which you've already seen in the textbook. And it makes sense because everything is identical to itself, so of course we can always assert that of any name. So that's our basic sentence here. Then we have an identity statement with two different names in it. That's going to be our second premise, and that is B is identical to A. Now, the second sentence here allows us to substitute A for B in the first sentence. So the first sentence is our Pn, the second sentence is our N equals M, and now we can substitute M for N in the first sentence. So we can substitute A for B in the first sentence, and we can substitute it for the first B, or just for the second B, or for both of them. But we've chosen here to substitute it just for the first B, so that gives us A equals B. And that's something that we need in the next, in a larger proof that's on page 57. But notice what's going on here. We can always get B equals B anytime we want it just by using identity intro. So if we've got the statement that B equals A, we can change from B equals A to A equals B. In other words, we can reverse it by using the rule of identity elimination in the way we just did. Okay, let's go on to our last, second last slide here. The example on page 57, where line 1 is A and A are in the same row, which is always true. Everything is in the same row as itself. Second thing we're told is that B equals A. And what we want to get to is that B is in the same row as A. Now we know that that's going to be true, but we can't get to this last line, same row BA, directly from lines 1 and 2, because line 2 is in the wrong order. Line 2 allows us to substitute A if we could find any occurrences of B in line 1, but we can't. What we need is this third line, A equals B. If we had that, then we could substitute B for A in the first line, and we could substitute it for the first occurrence of A, and that would give us same row BA, which is what we're looking for. So we're going to do the same thing we did in the previous slide, and here we go. Let's look at the final proof here. So our line 3, we're going to introduce B equals B, and our justification is identity intro, because we can always introduce any sentence of the form N equals N, meaning same name on both sides of the equal sign. Now line 4 lets us do what we did a couple of slides ago. We're using line 3 as our PN line, our first premise of the rule. We're using line 2 as our second premise. Line 2 lets us substitute A for B wherever we want to in line 3. So that gives us A equals B, because we chose to substitute A just for the first B in line 3. So our justification for that is identity elimination 3, 2. And notice that we have to cite them in that order if we're in the formal system F that has, where you have to apply the rules exactly. And you'll find this in the textbook too, on page 56, where it explains the rule. So we have to mention line 3 first because it's the line into which we'll be substituting. Then we mention line 2, which is always going to be the identity statement that has two names in it, like one name on the left and a different name on the right, because that's going to allow you to substitute the name on the right anytime you can find the name on the left. Then finally, we use line 4. Line 4 lets us go back to line 1 and substitute B for A in line 1. So we're going to substitute B for the first A in line 1, just because that was the goal of this proof that the authors gave us. We wanted to prove same row BA, that B is in the same row as A. Now we could have substituted B for both occurrences of A, and we would have got same row BB, or we could have substituted just for the second one, we would have got same row AB, but because the thing we were looking for, that we were asked to prove, is line 5, we substituted B for the first A in line 1. And our justification is identity elimination line 1, which is our PN line, and line 4, which is our identity statement with two different names on the sides of the equal sign. And I just have one other thing to say, and then I'm done here. In the formal system F, which is what these rules are really part of, and which is an absolutely unforgiving system where you have to use the rules exactly as they're formulated, this would be the only way that you could prove line 5 from lines 1 and 2. But in the software Fitch, where we're going to be doing a lot of our proofs, Fitch has what it calls generous uses of most of the rules of inference that you're going to learn, and that kind of means shortcuts. And Fitch actually allows you to go directly from lines 1 and 2 to line 5 because it doesn't worry about the order of line 2. It treats B equals A as being, you can use it as if it also said A equals B. So one of the things that confuses students about this section is that after you've learned this very rigorous way of doing the proof using the rule with perfect exactness, the very next thing they do is tell you, oh, but you don't actually have to do that in Fitch. But bear with them because they have good intentions here. They want you to understand the exact rules of the system, which are very rigorous, but they also want you to be able to do proofs more easily when you're working in Fitch. And so they do give these shortcuts. And in the end, you'll be grateful for the shortcuts. But there will be, on some quizzes and some exams, questions where you're asked to give a proof that would be correct in F, in the system F. And that means you can't use those shortcuts. And that's pretty much it. If anyone has any more questions about this, I hope this helps you understand the rule of identity elimination. Many of the rules you'll be learning are much more intuitive and natural, and you'll have less trouble understanding them. And I don't want you to be put off at the beginning when you're learning your first couple of inference rules by this one. So that's why I've explained it, and I hope that helped.